Oh, okay. Yeah.
Lecture number 4, we are still in flexible design of beams. We almost finished design and analysis of singly reinforced beams. We took some examples, how to find the cracking, how to find high cracking, how to find the elastic limit moment, and the nominal moment, and the ultimate, or the design strength. There are a few things, before I go into real example, design example, some notes, just to make sure you have a complete set of handouts or notes. Remember when I talked about the strength reduction factor? The T factor, strength reduction factor, I gave you the graph. I said there's for tight member, or ties, or spiral. I said the spiral, that's for more columns. The ties, that's beam, depending on the stirrups for the shear design. So it starts at, looks like that, right? This is the strain. And this is the Phi factor, the strength reduction factor, based on the strain in the steel at ultimate. If we have a strain more than 0.005, we're talking about tension control sections, right? If we have more than that here, the Phi factor become constant, equal 0.9, and that's the maximum. And that's the maximum you can get. Then we said if the Phi factor is, if the strain in the steel at ultimate is this than 0.002, is also the Phi factor become constant, and it's equal to 0.65 for members with ties, or 0.75 for members with spiral confinement to the main steel. Then we said between them there's a transition. If the strain in the steel at ultimate, in the tension steel, is between 0.002, which is the yield strain, and 0.005, the Phi factor is calculated from an equation or linear interpolation, right? You have this. You should have this in your handouts. And okay, so what's the equation for this one? If it's in between, once you calculate your strain in the steel, the actual strain in the steel from the strain distribution, what's this value? Phi equal 0.65 plus epsilon t minus 0.002, 200 over 3 for this. And for the spirally, Phi equal 0.75 plus epsilon t minus 0.002 times 150 over 3, or 50. Okay? As you can see, guys, well, this is just linear interpolation. That's what I'm doing. So if it's 0.002, it's 0.65 because this is 0. And that one is 0.75. And if the strain is 0.005, this will give you 0.9. And this will give you 0.9. Good? Good? That's the equation. So once you get this one from the strain distribution, you can come and, if it's in between those, you calculate your Phi factor, you multiply it by Mn to get the design strength. Or there is a short way to write this one. Phi equal 0.48 plus 83 epsilon t. And here, Phi equal, sorry, yeah, that's true, 0.65 plus 50 epsilon t. You can check, they should give you the same answer. This subtraction, this is how they add. Okay. You just rearrange this or reorganize this. That's the strength reduction factor. Good? Now, going back to the singly reinforced columns. We said there is some terminology in terms of the failure mode, right? We said there is something called tension controlled section. What do you know about it, guys? When I tell you tension controlled section, what do you know about it? Epsilon in the tension steel at ultimate, what is it? Greater or equal 0.005, or at least 0.005. What else do you know about this failure mode? That's a good failure mode. The ductility is 2.5, which is at least 2.5, which is 0.005 divided by epsilon y, which is 0.002. What else do you know about this? 0.9. The phi factor is 0.9. Good? Now, compression control sections, or compression control failure, or compression failure. Section or failure. What do we know about this thing? We call it compression control. What do we know about it? Epsilon T is what? Steel did not yield. Steel does not yield at ultimate. It means the strain and the tension steel is what? Less or equal 0.002. Now this 0.002, guys, it's stuck in your mind. That's the yield strain of steel. We're talking about the grade 60. Grade 60 KSI steel. Most of the steel is used 60 KSI. So what do we know also about this one? What's the phi factor? 0.65 tied, or 0.75 spiral. That's the confinement. Good? What's in between, or transition? Transition, it means the steel yield. The strain in the steel is more than that. Right? That's a transition. The phi factor is calculated using these equations. Good? Now, you may ask another question. Now we know here, what's the design strength here? What's the design strength? Phi mn. When I say the design strength, it's phi mn. When I say nominal strength, mn. What is it here? Just write the formula. Equal 0.9. What else? AS. Is it FS? Is it the stress in the steel? We know it. It yielded. It yields at ultimate. So this is AS what? Fy what? D minus A over 2. Right? And we know A equal AS Fy over 0.85 F prime C B. We know that. Good? Now what's for this guy? What's phi mn for this guy? For tide, let's say. For tide. You can tell me, okay, I know the phi factor. What is it? For tide columns. Oh, sorry, for tide members. Actually, we call it column, because when you have a compression failure, that's more into column action. Members with strain in the steel at ultimate less than the yield strain, these are typically columns. In between is a transition from column action into beam action. Column action into beam action. Later on, I will explain you in details when we talk about the column interaction diagrams. When we have an interaction between axial and bending, what's happening? If you have the case of pure bending, that's beam. If you have a case of pure axial, that's column. In between, there's an interaction. What is this? You say, okay, 0.65. If it's tight, talking about tight, it's 0.65. What else? AS. What else here? FS? Of course. It's less than Fy. AS, FS. D minus A over 2. Now, one more unknown in this equation. This type of failure, you really don't know what's Fs. So where do you get Fs? Anytime you need one more equation, that's equilibrium. Here, this is from the equilibrium. T equals C, and finding the moment between them. Look, T equals C, that's one equation. Some of the forces in the x direction equal to 0. You get T and T equals C. Some of the moment at one of them is AS Fy D minus A over 2. That's the moment equation. Anytime you need one more equation, now, is there anyone for Fy? Yeah, that's for the shear later on. Now, anytime you need one more equation, more than the available equilibrium equation, what do you do in mechanics? We go into something called compatibility, right? We go to the strain distribution, or can we relate the deflections together? Compatibility, strain distribution. We get this from there. How? Because we know this, the steel is in this behavior. If this is the stress strain diagram of the steel, elastoplastic, we are here. It did not yield. This is the idealized stress strain diagram for a steel. This is what we use for the design. The stress is here, somewhere in here. It means Hooke's law is valid. It means Fs equal what, guys? Equal what? Hooke's law. E epsilon s. E times the strain. So where do you get epsilon s from? From the strain distribution. This number is still fixed. Beams will fail when the strain in the concrete, when the compression strain in the concrete reaches 0.003. Fixed point for analysis. Now you look at the steel. What's the strain in the steel? Did it reach 0.005? Tension control. Did it yield? Something else. Is it less than 0.005? Compression control section. So this point is a reference point, given. No, without it you cannot solve it. Without this one we cannot solve. We have one more unknown. We need to find something else. So this is defined or considered by the code. So that's your steel. That's your epsilon s. This is what? C. And this one? D minus C. What do you want? Epsilon s. Right? So epsilon s over D minus C. Look at this again. Epsilon s over D minus C equal epsilon ultimate, which is 0.003 in the concrete, divided by C. So epsilon s equal D minus C over C times 0.003. Similar triangle. If you don't know similar triangles, go back to calculus. Right? So epsilon s equal 0.003 D minus C over C. Do you know D? Yes, given for analysis. Given for analysis. Do you know C? Do you know it? I don't know it actually. Does anybody know it? How? How are you going to get C? Wait, let's see Gerald. Do you know C in that equation? If you know C, that's it, you solved it. If you know C, we get this. We have Fs equal Es times that. We do that. Do you know C? You don't. Where do you get C from? Anytime you stuck, what do you do? E equals C. We need to get A. We need to get A. A means C. Why? Because the relationship between them is a material factor. It depends on F prime C, that beta 1. A equal beta 1 C. That beta 1 known. Once I give you F prime C, you know beta 1, right? And we said F prime C equal 4 KSI, it's 0.85. Less than that, 0.85. More than that, decreases. Greater than 8 KSI, stops at a certain number. Good? Between them, there's a function I told you about. You have it in your notes. So look what you have. T equals C. Tension equal compression in the concrete. That's the big C, the compression in the concrete. So what's T? As Fs we said. Equal 0.85 F prime C B A. What's A? Beta 1 C. What's this guy? AS. What's Fs? ES epsilon S equal this. What's epsilon S? 0.003 D minus C over C equals that. Is it easy equation, Paul? You good with math? That's a quadratic equation. With C. We need to solve a quadratic equation for C. Once you get C, you get A, you do that. That's compression analysis. That's for analysis. You are not allowed to design any new section to be compression controlled section, a beam, not allowed by the code. At least rho must ensure that the strain in the steel be 0.004, which is rho max. We agreed on this, right? For any new design, not allowed. But you may come into an old beam. You want to analyze it and check. So this is how you do it. If the strain will not be more than 0.002. If the strain is more than 0.002, means the steel yielded, means Fs equal Fy. Below that, you are in the elastic region. That's the analysis of compression control section. So easy, not a big deal. The only thing is just the quadratic equation, you just put it in the calculator and done with the new calculators. Or just solve it. You know guys, you know now. So how am I going to do it? How am I going to... You know guys, C is around 0.3D, 0.4D, right? 5 inch, 3 inch, so just something. That's the first, you can guess this one and see where you are, right? By trial and error if you don't want to go with the solution of the quadratic equation. Okay? So that's for analysis of compression control sections. And some notes on what we have, the definition of the failure modes, the various failure modes. Good? Any question? Ready to start the design? That's all what I can give about singly reinforced beams. About singly reinforced beams. Go ahead.
You said that for the design, the strain in the steel has to, like the minimum allowable strain in the steel is 0.004?
Yes.
Okay.
We like to, you are encouraged by the code to have at least 0.005 to have tension control section. But the code is telling you, you can go with 0.004. However, if you compare the strength based on the ACI calculation, that you will get, look, to get 0.005, you need less steel than having 0.004. Because more steel, less strain. Right? So for the 0.004, which is the maximum allowed by the code, you will have more material, more expensive section. When you do your analysis, that 0.004 will give you phi less than 0.9. Will give you higher MN, by the way. The MN will be higher, of course, more steel, higher M. Right? AS is higher. AS Fy d minus A over 2. But phi times that MN for the 0.004 compared with phi times MN for the 0.005, this may be more. So you're putting steel for nothing. That's why you are encouraged to have tension control section. 0.005 and more, so that you can get the full phi factor, full strength. We can check it. When we have one of the examples, we can check it if you want. Or design with the rho max or rho 0.005. When I say rho 0.005, strain equal 0.005. Good? Let's take one example. Which is going to be 4.18. That's question in the textbook. It says a rectangular tension reinforced beam is to be designed for dead load of 50 pounds per foot. Dead load equal 500 pounds per foot plus self weight. So the dead load will be 500 pounds per foot or 0.5 kg per foot plus the self weight of the beam. And live load equal 1200 pounds per foot. These loads are service loads. Anytime he gives you load, if he doesn't say the word ultimate loads, they are service loads. They say load, service load. Ultimate loads or factored loads, that's it. If he doesn't say the word factor, They are service load. Span, simply supported span equal 22 foot. Fy equal 60 KSI. F prime C equal 3 KSI. H max, same, the maximum depth cannot be greater than 16 inch. It's given. H max cannot exceed 16 inch. Calculate the required beam width and tensile reinforcement. Design B and AS. Given that, using rho equal 0.6, rho 0.005. He's saying assume D equal H minus 2.5. Of course, use the ACI equation. Okay, guys? Okay. This is what's given. So we have a simply supported beam. This is the loading. And the span is what? 22 foot. Okay? First thing you do is you need to analyze it. Before you design, you need to find what's M ultimate from analysis. To find M ultimate, you need to find W ultimate. Because these loads are service load. Okay? Saying that it's 500 pounds per foot plus the self weight of the beam. How much do you think the self weight of the beam will be? How much? It will be sizable here. Yeah. Think about it. He's telling you H is 16 inch, right? So H is 1 point, whatever, 3 over 12 inch, 1 foot, 312 or 412 foot, 1.33 foot. So B, usually B is 1 foot. Just, this is assumption. You assume. Once you design, you check. Is the moment when you consider the actual dead load or the actual self weight. Do you need more or not? We did this in the steel for those who took steel, right? Or the self weight. Just to give you an idea how much to assume. Just to give you an idea how much to assume. So if we said like 1.33, that's H. If I'm going to use H, the full H, 16, right? And assuming B equal 12, could be more than 12. So that's the cross-section area is 1 times 1.33, which is 1.33 squared, right? Times the unit weight of concrete, which is 150 pound per foot. That's give us the answer. So assume self weight equal I'm going to assume 200 pound per foot. You're going to say, how do you get this number? 200, 250, 300, depends. You can assume whatever you want, but you need to check it. I'm going to assume 1.33 times 150, that much. I may get B more, I may need a bigger B. Then I will check it, and then I will show you how we check. That's just an assumption. So total dead load is what? 200 plus 500, right? That's 700. So now W ultimate equal 1.2 dead plus 1.6 line equal 1.2 times what? 0.7 plus 1.6 times 1.2. That's in kip per foot. So W ultimate equal, the 0.7 is the 500 plus 200. W ultimate equal what? You guys need to do the calculation with me as I go. Everybody. Get the answer.
2.96.
2.96. 2.76 kip per foot. What's ultimate? Andrew. What's ultimate now for a simply supported beam, distributed load? What? WL square over 8. 2.76 times 22 square over 8. Ultimate equal what? That number over there. 2.76.
167.
167 kip foot. That's structural analysis so far. All of this is structural analysis. Now we need to design. A structural engineer gives you this moment. He's telling you design. That's what he gave you. The philosophy of the design is the following. Look. Ultimate. You see it? That's the design. Less or equal phi mm. Wherever you have internal force from the actual load or the factored load must not exceed what you're going to get from the strength of the cross-section. This is how much the cross-section will give you based on the ACI code. This is how much the loads will put in your section. Good? The section must be stronger, must give you more than what it will be exposed to. That's the philosophy of the design. If you design for shear, V ultimate less or equal phi Vn. P ultimate axial less or equal phi Pn. Good. Now, where you start? By making them equal, right? By making them equal. Then you get something more. You add little bit. But you know, this is known to us. It means this is known. Once we have the formula for that. So what's phi Mn equal? Equal phi. We need to check it. As Fy d minus A over 2. Put the formula there and see what you have. Put the formula there and see what you have. In the question, he said use, what did he say about rho?
0.6.
The ratio of steel. He said use 0.6, rho 0.005. That's what he told us, right? If we use rho for 0.005, what's the P factor? 0.9. If we use less than that rho, we still get 0.9 because the strain will be more. Good? So this tells you what's the P factor? 0.9. Good? So what's rho 0.005? Can someone calculate that? Sorry. Some guys in the exam, for some reason, they will put rho equal 0.005. Which table in the appendix?
8.4.
8.4. Table A.4. Or you can calculate this one. We have the equation for it. For rho 1.005. We derived that, the other lecture. But you have it in the design aids. Right? You have it in the design aids. Rho 0.005. What's your F prime C? 3 KSI. What's your Fy? 60 KSI. You go there, you got rho 0.005 equal
0.0135.
0.01, like that?
135.
135. Now use what? 0.6 times this number. What do we get? Our rho equal 0.6 times that. Guys, in the exam, don't write me, use that. Get everything. Keep going with the calculator.
0, 0.
Don't tell me open book, I need to just read. Open book means you solve. You already have everything.
0, 0, 81. 0.0081.
0.0081. He wants us, the question wants us to use that. That's the ratio. Right? That's what we need to use. That's what we need to use. 0.0081. Now how are you gonna go now? What do you do? How you proceed? How many ways I taught you, or how many shapes of the strength or phi mn I wrote for you the other day? 3, right? I told you phi mn equal phi a s of y d minus a over 2 and a equal a s of y over 0.85 that. Then I combine those into one formula, right? I told you phi mn equal rho b d squared f y 1 minus 159 rho f y over f prime c, right? The only unknown in that equation is that I said rho b d squared f y 1 minus 159 rho f y over f prime c. There's two unknowns in there. Rho and sorry. Remember that? I said phi mn equal our phi we agreed how much? 0.9 rho b d squared of y 1 minus 159 rho of y over f prime c. Right? Did I write this equation for you guys? Right? What's the unknown in this equation now? In this part here, in this part, to calculate this guy, what's the unknown in here? Do you know rho? 10081. Do you know d? Yes. Assume d equal h minus 2.5. So 16 minus, if we use h equals 16, the maximum depth. So we have d. We have the maximum. We try always to maximize d. Why? Maximize h as much as we can. Why?
Higher moment of inertia.
So it's deflection. It's deflection. Smaller steel. Smaller steel. More concrete, smaller steel. Steel is more expensive than concrete. Good? So D is known. He wants us to calculate B. Okay, unknown. Rho, just calculate Fy, F prime C. So, look at this. What's 3mm? We want this one to be more than what? Than that. So I'm going to put them equal and select something on this side more than what's the equal part. If I put 176 in here, right? 176 or 67?
167.
If I put 167 here, right? I'm going to calculate B exactly, that will give me that number, right? What if I increase B a little bit? I'm going to get phi mn greater than an ultimate. Right? So 176. Then you need to change this one into inch, pound. Always multiplied 6. This is in kip, foot. Sorry. Sorry. That's in kilonewton meter. I'm changing kilonewton to newton millimeter still. This is in kip, foot. We need to multiply it by 1200, right? To change it into pound, inch. Pound 1000, or kip equal 1000 pound. Foot equal 12 inch. Equal 0.9. What's rho? 0081. What's B? We want that. What's D? Here. Use H equals 16 inch. It means D equal 13.5. So times 13.5 square. Don't forget the square. If you don't square it here, D B, by the way, contribute a lot to the strength. If you miss that, you need big B. It's the depth will give you more moment, which is also inertia. Strength comes from the depth. Times 60 what? You need to have this one in PSI. If you want to have this one 60, this multiplied by 12. Just compatible with the dimension. So this is 60,000. This 1 minus 0.59 times 0.0081. So times 0.0081 times 60 over 3. You're going to say, no, it's 60,000 over 3,000. Doesn't matter. When you divide them here inside here, they cancel each other. You solve for this one, you guys get B. You get B, the minimum B you need to use. That's the minimum B you need to use. One equation. One way of doing it. That's one way of doing it. That's based on the calculation. Did we use any design aids so far? None. We just use it for calculating 0.0 to get 0.005, which we can calculate from the equation I gave you. Right? Based on that, what did you get? Let's see numbers. Numbers. I need numbers. 20?
28.
28 inches. You get that number? At least 28 inches. Right? I need B at least 28 inches. If I use 28 inches, remember what's going to happen to the self weight? Will be high. The self weight will be high. Okay? I need another round. I need to be careful. If I go with 28, I need to be careful. For sure, the section will fail. Right? Because this was assumed based on B equal 12 inch, whereas the self weight was assumed based on B equal 28. Then, revise. Self weight. For that B. For that B. Assume B equal, whatever you want to go with 30 now, or 28. Assume B equal 28 inch. And H equals 16 inch. This will give you self weight equal, you know how we do it, guys. 28 over 12 times 16 over 12 times 150 pound per cubic foot. We change the 28 to foot, this to that. How much you get the answer?
467.
467. 67. Assume 500 pound per foot. Assume 500. I don't want to go back one more round. Not a big deal. I bumped this one from 467 pound per foot into 500. That's a design. Yes, you can open your eyes. That's a design. That's a design. It's not, we are not selling gold. If you increase B and D, you decrease the steel. It's a balance. Good? We're not selling gold in here. If you are designing with gold or whatever expensive material, okay, just bring it to the 1 millimeter. If you want. Remember in the design, I always tell you, as long as your fee MN not more than 10% what you need, you're good. So I think we are within the room even if we increase this one little bit. So now what's W ultimate? Fast, you do it fast. 1.2 times 1. Now 500 plus 500, that's 1. Plus 1.6 times 1.2, right? So W ultimate equal, what's that number? 3.12 kip per foot. I'm ultimate. This number times 22 square over 8. That's why you need to bring a calculator to this class.
188.
188. Guys, listen. This is not an easy class if you don't follow up. You don't want to flunk this class. You wait one more year. You listen to my advice, you bring a calculator, you get every number I ask you to get. Typically, we have 2 to 3 students every time I teach this course, flunk this course. You don't want to be this one of those 2 students. 188, you said? That's what you got?
Yep.
So, say, you guys, you go back here right away. You go back here right away. 188. You get P. 188 to get P. I'm not going to do this calculation. Once you do that, what's P? The only thing that will change is this. Everything else is the same. You get? So this is the same. So what you need to do is B equal what? For 176 we needed 28. For that, B equal 188 over 28 times, over 176 times 28, right? Right? So B equal what?
31.3.
31.3.
But I calculated out a long one.
What do you mean?
I mean, I solved for B based on a new MU.
Yeah, you just should give us this. Did you get this? When you do this? Same, right? Almost. 30? What do you get?
31.7.
Well, 29.9.
If you do this? What if you guys do this? That's what he did.
31.3.
So that's the actual number. Because I know it's not linear exactly.
Okay.
So the actual is 31.3. Now what's the self weight now?
What is 12 like?
How much? Is this that one 500? We are okay.
121.6.
500?
21 or 522.
You need to have one more round if you want to keep going this way. Bump it to 32 if you want, or 34, and you keep going. Okay? And you keep going. Use, let's assume, use.
So, like, use a software at 600.
I think 32 will do it. That's 32, how much? The moment here, you can calculate that. B equal 32, these are our values. Let's go back and check. That's not a normal beam, guys. Usually when we design, we have H, we like to have H 1.5B or H between 1.5 to 2B. But here you are limited by the architect to 16 inch. That's why you ended with something like that. But usually you have B 10, 12, that much. And you have D higher or H higher. How much you get for? Did you get the number when you have, if you plug this 132?
Well, our new MU has to be 192 is what I was thinking.
192?
Yeah.
Why 192?
Like the 176 times 12,000, that 176 is the MN, right?
It's 167, it's supposed to be 167.
It's, well, okay. But either way, if you make that number 192, then we can
Did
call
we make
it.
a mistake?
No, it was 167 to start with.
So it's wrong. Yeah? You guys never stopped me. Right? This is 167.
Still.
But I think we've still done all, I think we've still done all our
It
numbers.
gives you 28.
So that's what based on that?
Yeah.
So yeah, that's good. So that's it. The 28, so our calculation is correct. But this one was 67. Good. So now let's summarize our design. Design, at the end of the question, we sketch your section. So I know you can get numbers, but show me the section. Not done. Not done. So our D is what? 13.5 inch. Our H is 16 inch. Our B is 32 inch. What's our AS? What's AS? Area of steel. What is it? Rho ED equal 0.0081 times what? 32 times 13.5. That's how much steel you need. What's AS? Three?
3.5.
Inch square. Right? This, I'm going to tell you why, even if we need a little bit more than that, why we are okay. Why we are okay. I'm going to show you in a minute. Now, is this a final design? If he's asking you calculate AS, that's the end of the question. That's the end of the story. That's not a design. You tell a guy in the field, use 3.5 inches square. He'll tell you, how many bars? No, it's 3.5. How many bars? What bar size? Select bars. Where do you go? Table 8.1 in the appendix. Give me something, number of bars that will give me 3.5 inches square.
What table is that again?
The first table in the appendix. You have the bar diameter, right? So the first table, guys, in the appendix. So next time you bring the design aids with you. Okay? Now listen. In that table, what do you have? You have for one bar. Good? That's the information about one bar, right? One bar. Go to the next table. Now look what do you have in that next table. The second one. Now you have a combination. He tells you, based on whatever combination number of bars, how much you get. Give me the best, the closest to that, so that we are economical. If you can get 3.5, perfect. That's what you need.
6 number 8 is 3.52.
Let's see the options. He's saying, Paul's saying, 6.
Or 8 number 6s, I'm sorry.
8 number 6.
8 number 6s is 3.52.
So he's saying 8 number 6 equal 3.52. What else? Is this the closest? 6 number 8. You know, the first one is the number by the US system. The second, SI, that's the millimeter, equivalent millimeter. Forget it. That's in millimeter. Second table. You see it? So he's saying number 6.
8 alone is 3.52.
Very good. And how about anything close to it? Because you may end up with a problem fitting 8 in that section. In this section you will be fine. You may end, if it's 12, there is no way you can fit 8 bars of number 6. The spacing, you have a spacing problem. So that's always, get some combinations. Anything closer than this?
If we use,
I like number 8 and 7 for beams, guys, even number 9. But that's fine.
I mean, if we use 5,
Well, just tell me. Don't
I mean,
combine.
I
Don't
would say
combine.
no, if we use
Never combine unless you have to.
I mean, if we use the level number 5, we get less steel, which is better, but
How much? Less than this. What you get with 11 number 5?
3.4.
Not good. You need 3.5 at least.
Well,
You can't. If you use this steel, your VMN is this than that. That's why you try to get more than what you need, so that even if B was at the edge, you still bump the strength with the steel. You have no way. I mean, this is a good thing here. It's exactly there's something give you 3.8 something, right?
Well, I mean, there's all kinds.
There's 3.8.
Yeah, 3.81 would be 3 number 10s.
Yeah, that's 10 is too big. Too big to cut and fit in. That's good. So you get, what do you get? What do you select? The closest to the number you have. The closest highest. The first highest. Given that you can fit them. Given that you can fit them. So that's what we have. And now you can go back and calculate VMN little bit more because of this. Little bit more because of this. And our row, we kept it at around 0.6, row 0.005.
Right. So we're using our H as 16 inches.
Yes.
And then there's a 2-inch gap, right, before any of the...
2.5 to the center of the steel. I'm going to draw the section for you.
Okay.
Section will look like this.
My question is, can we use 2 rows to get those number 8s, like 2 rows of 4? Is that how we have to
You
do
have
it?
to.
Oh, okay.
The section is so big. We'll see. Section is wide. Section will look like that. How many bars we said we have? 8? That's what you expect. When we do stirrup design, we'll design this. So those are number 6. Now you can, as you said, look, what's D to the center of the bar, not the stirrup. This distance must be equal 16.5, sorry, 13.5. And the cover down, 2.5. You can say everything is in inch. Okay? That's how the section will look like. Whatever we have at the top here, that's for constructability for this section. We don't need it. Because we have positive moment. So in the supported beam. Good? Now, what's the spacing? Just to check the spacing between them. The side cover usually is similar to the bottom cover. The side cover here, typically equal to the bottom cover. So 2.5 inch from both sides. So we have 32 minus 5, which is 2.5 from here and 2.5 from here. How much? Divided by 7 spacings. Spacing. How much?
I got 3.86.
32 minus 5 divided by 7. That number, how much you get?
3.86.
3.86 inch. Is this good or not good? To the center, by the way. To the center. Right? This is between them, to the center. What's the clear?
2.67
Equal what? 3.86 minus what? Half the 6 from here and half the 6 from here. We said, what's the diameter of number 6? 6.8. So minus 6.8. That's 3.68. How much?
3.1.
Is this good or not good?
Yeah.
Why?
Yeah. Well, it's more than 2.5 inches.
Smart. Even if you have no clue what the spacing is supposed to be, this is more than the cover. If it's more than the cover, it should be good. Then we have no clue what's the closest. But how do you think what's the closest should be? Remember? Based on the aggregate size for constructability. What else? Corrosion. Is this member outdoor, indoor application? Is there the icers? Is there something for corrosion of steel? That you may need to increase the cover. Like that in bridges. The cover should be at least 2¼ inch over the steel. In bridges, the top. And there's a sketch which tells you what's that. And usually, just for good to know, usually the clear spacing is bar diameter equal the bar size, 1 inch, 1.33 diameter of the aggregate size within that range. 1.5 the size of the bar, 1 inch, which is based on the maximum aggregate size if we're using something, let's say 3/4 inch. Okay? This is given information. This is given information. You go to any sketch, you will see this in the ACI code. Chapter 1 or 2. The one that we skipped because it's background information. Okay, guys? Okay? Just keep in your mind. Just take it like that. At least equal to the cover here. And usually the cover is 2 inch to 2½ inch to the center of the bar. So the clear cover from the bottom here, you know how much the clear cover from the bottom? The clear. Clear, it means over steel. We have 2.5 inch, right? Minus 3/8, which is half of the bar diameter, right? Minus the diameter of the stirrup, which we use usually number 3. So 2.5 minus 3/8 minus 3/8. That's over the stirrups. If I tell you in the question the cover over the stirrups that much, it's different than when I tell you the cover over the bars that much. Or if I tell you the word cover, we assume to the center of the bar. So usually within that, the spacing is 1.5 inch, something like that. 1.5 inch, 1 inch, that's the closest you can get. Sometimes you can go to 1, if you know that your aggregate is less than 1 inch. Okay guys, that's a complete design. That's a design problem. Is it time? Okay. Now, what if we want to design this one with the design aid? Look how easy things. Look how easy. One step. 1 or 2. Let's see. What's an ultimate equal from the beginning? Or if we assume the right thing, what's an ultimate approximately?
67.
After that, let's say we went to
192.
around 192. Around 192. Input. You can check. But assume that ultimate is known, right? For any ultimate, you may go with the second round. What's ultimate? We said equal this or equal phi mn, right? And phi mn equal what, guys? You remember this? Look at this. 0.9. What? B d square. What? R, which is this in here. R, 4 rho equal 0.0081. There's a table given for you in the design aids. Is it 4 or 5? 5. There's a table in there, in the appendix. For if you know rho and you know f prime c and fy, you get r directly. So easy. What's r? 10081. To your best.
435.
435.
Yeah, 435.
435. And that's in psi. The unit at the top in psi. Okay? So if this is the case, look what we have now. This is what the case. Then BD square, guys, BD square equal ultimate. This is ultimate, we said. We're going to make it ultimate. Equal 192 times 12,000. We change it to foot to pound inch divided by 435. Right? Right? So you get a number in here. Now, if you don't know any of them, like typical question, you don't know any of them. In this question, he gave us the maximum h that we can use, 16, so we knew d. But if you don't know any of them, again, there is no limitation on them. I told you, we like to have d between 1.5 to 2b. Right? Given that, you will find a b enough to accommodate the bars. So you can fit the bars in there. In this case, you can get that, then you can get b equal that answer divided by d squared. You get the same answer. That's what we get. See, the design is much easier. You don't have to worry about this equation. Or you can do it this way. as of y d minus a over 2 by assuming a. That equation, if you put 192 equal 0.9, now you need to assume b, right? You assume b, you get as, because rho you have it. You check. If it's this, you increase it. Trial and error. That one, the first equation, the one it has Pmn equal a 0.9 as of y d minus a over 2 and a equal as of y over 0.85 of prime c. You need trial and error in there. Trial and error. Design aid or this equation. 3 ways to do it. That's a design problem with structural analysis. If I give you design the following beam for this ultimate, you don't have to worry about this. If I tell you self-weight is included, it means it's included. Don't assume anything. This question is it without the self-weight. Some terms, guys, are easy, but I know since it's your first experience with this, self-weight not included, self-weight included, it's so easy things. Either included or not included. What to assume, as I told you, 200, 300, 400, we're not selling gold. As I told you, you don't have to get it exactly. And when the question is telling you, design so that rho equal 0.6, rho 0.005, it doesn't have to be exactly, unless it tells you, I want exactly that number. Within that range. Within that range. Don't try to make it that. You cannot. You would find the steel that will give you that number. Around that number. Okay? A question which is a preparation for the next class. Nice question. Which will be question okay, you know what? Let me just do this for you. Question 421. He's saying a 4-span continuous beam of constant rectangular cross-section. So 4-span, constant rectangular cross-section. So the cross-section will make it continuous. What do we change? We change the steel. If the beam is continuous, why we change the steel? Because we have positive moment and negative moment, right? Cross-section is supported at A, B, C, and D. Sorry. So this is what we have. Beam like that. 2, 3, 4, 5. That's 4 spans, right? Is this determinate or indeterminate beam? Of course indeterminate, right? 2 unknowns, 3, 4, 5, 6. You have 3 equations indeterminate to the 3rd degree. However, he's done this for you. Right? He's calculating you the moments. By the way, it's fixed even here. Look how bad this thing. A, B, C, D, E. However, again, he did the analysis for you. You go to the E tabs. You guys are expert now at the E tabs. You run the analysis, you get all the results. 138. The moments are in kip foot. 138. 220. 200. 220. 138. 158. 138. 138. 158. These are the moments. These are the moments in kip foot. So he's telling you to design this one. He's giving you everything you need. He's telling you use D equal 1.75. P, F prime C is given. Fy is given. And he's giving you rho. He's saying use 0.6. Rho 0.005. Same question. Right? Design is the same, same concept. But look, it has some structure. That's why we stress on understanding structural analysis. If you don't know structural analysis, you cannot go with any design. With any design course. So we have moments here, right? When you have the moment at the support, guys, the moment at the support are what? Negative or positive? Yes, have courage, you cannot miss this. Negative. It means tension at the top. It means where is the location of the steel at the support? Top. Top. Negative moment, tension at the top. When you have positive moment, which is within the span has positive moment, tension at the bottom. Right? So this span has 158, 138, 138, 158. Positive. Their reinforcement must be at the bottom. And these supports, they have negative moment. Here, 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 with these values. Guys, why are you looking at me? This is the moment diagram. Negative, First support, second, second, second. Positive, negative, positive, negative, positive, negative. Positive, negative. 138, 158, 220, 138. Positive, negative, negative, positive, negative, positive. Support. You have a support. This is how the beam bend. Tension at the top. Span. That.
I'm sorry to ask this, it's gonna sound dumb. Those are pins in the middle, how do they change the moment at all? I don't understand, like, if they're pin supports to the
Is
center.
that, look, is this pin or roller?
Well, it looks like a pin with a roller under it.
This shape to you, is it a roller or a pin?
I always thought it was a pin with a roller under it. Is that a roller there?
Paul, see this support here?
Mm-hmm.
The beam is going over it.
Okay.
So look, that's the support. The beam is over it. It's not broken into two pieces. It's not an internal hinge we're talking about.
Okay.
Okay? The beam is one segment.
It's just setting on span.
Exactly. It's not an internal hinge. It's just over it.
Okay.
Okay? So whether we do it this way or that way, it's a roller.
Yeah.
The internal hinge, you see it like that. It means the beam is two segment. It means at this point we release the moment.
Mm-hmm.
It's a free to rotate. Good?
Okay.
So these are the. So where do you start? He's saying the cross section is the same. The cross section is the same. Where do you start? Well, with which one? The maximum. You use the maximum moment, whether it's positive or negative, to get your cross-sectional dimensions. Right? For the 220, you get BDAS. He's giving you rho equal, use rho, that number, right? Do you guys have rho 0.005? If I give you f prime c and fy. Yes. You go to the chart. You get rho 0.005. Good? You calculate rho that you need to use, which is 0.6 times that. Once you have rho, Austin, you go get R. Right? And you know your phi factor is 0.9. Once you get R, I just wrote it. Here, you calculate BD squared based on the 220. 220 times 12,000 divided by 0.9 times R. You get BD squared. He's telling you there is a relationship, he wants that. You substitute one into the other, you get B, you get D. Once you figure out your section, B and D, and add a color to one, say, assume 2.5 inch color, you get B and H, right, for your section. You pick a steel for that moment, which is for this and that. You pick a steel, right? Then you go to this, and that steel must be top. Say like 5, number 7 or whatever. Then you use the same section. You plug into that equation 158 and 158, and that's how much steel you need at the bottom here. Then you check how much steel you need for that and that, or for the 200. You may end up with the same as that one. Right? That's the design. That's how we do it, guys. This is the real. I mean, most of the beams are continuous beams. And this is what you're going to have. Let me do it this way. Just to show you. Usually this is fixed because it's going into a wall or into fixed with a column, the end. Let's make it a little bit longer. Okay, and that's one support in here. And there's another support in here. And there's one here. Is there one more in the middle? 3, like that. Okay, so that's what you needed here. Negative here. Positive here. Negative here. Positive steel. Negative. Positive. Negative. Positive. Negative. The negative cannot be like that. It must be anchored to create a fixed support. How much we anchor it? Development length, chapter 6. To calculate this. this must be anchored to give you a fixed end, but must be top, bottom, top, bottom. So how do we do it? Okay, here, how much you get this into this support or into this support? Because remember, this is a column. At least 15 centimeter, which is 6 inch. At least must go into the column 6 inch. This is steel. There's requirements given. There is sketches given for you. Now you may say, okay, I need 5 number 6 here, 3 number 6 here, 4 number 6 here. Look at this fall. Again, the last thing I'm saying. You may need 5 here, 6 number 6 here, 8 here. You run the minimum all the way. You don't have to cut. Let's say the minimum you need for the negative is 3, number 6. You run those bars all the way. Then you need 2 more in here, you put 2 more. You need 1 more in here, you put 1 more. Like, same. Every beam must have at least 2 bars go all the way. By the way, in the previous question, we just last one thing you need you guys to check is just to check row minimum. Check whether row, the one that we use 0.6 row 0.005, must be greater than row minimum. We know it's less than row max because row 0.005 is less than row max, which is for sure it will be more than row minimum. But that to complete that question, you must check row against row minimum. Good. So you see, structure. Don't be scared. Structure. Don't get scared from structures. Moments are given for you. Positive, and still at the bottom. Negative, still at the top. You just calculate based on the equation that's given for you. Next time I'm going to explain to you the doubly reinforced. The next subject will be doubly reinforced. It means you have a compression steel. You have AS dash. What do we do in this way? How we calculate the strength when we have that? We have steel in the compression zone. In the tension we have T, right? Tension. In the top what do we have? C, right? We said T equals C. In this case, what do we have? Tension, compression from the concrete, compression from the steel. So we'll have T, C, CS, or CS dash. Compression from the steel. So the equation will be T equals C plus CS dash. Then we're going to have the strain, compression steel. We're going to have to check that compression steel yielded or not yielded. That's the only problem. If it yields, so easy. If it doesn't yield the compression steel, we need to do one more equation. So I'll see you guys this Wednesday. Doubly reinforced. Don't miss. That's the most difficult subject in this class. Doubly reinforced. Doubly reinforced. Don't miss this class.